Hello everyone and welcome to this presentation. My name is Imran. I am presenting our work on deep learning based prediction of energy decay curves and reconstruction of room impulse responses. This work is a part of our research towards fast and accurate room acoustic modeling, and today I will walk you through the motivation, the methodology, the model and evaluation results. Here is a quick overview of the talk. I will start with a short introduction to room acoustics and why predicting room impulse responses is challenging. Then I will present the dataset and the simulation pipeline that we use to train our model. After that, I will describe the LSTM-based architecture and how we process the input features. Next, I will show how we reconstruct room impulse responses from predicted energy decay curves. We will look at both subjective and objective metrics. We used Mushra listening experiment for evaluation of perceptual metrics. Finally, I will summarize conclusion, discussion, limitation, and outlines for some future directions. Room acoustics have a significant impact on how we perceive sounds in everyday environments, for example, concert halls, classrooms, offices, and even virtual reality spaces. Important acoustic parameters such as T20, T60, EDT, and clarity indices describe characteristics like reverberation time and speech intelligibility. Traditionally, these are obtained either through direct measurements or costly simulations like ray tracing, the image source method, or wave-based solvers. All these methods are computationally expensive, especially when repeatedly predicting acoustics for many rooms or in interactive applications. The challenge we address is the high computational cost and complexity of predicting full room impulse responses from scratch. Instead of directly predicting a high-dimensional RIR, we focus on a more compact representation, that is energy decay curves. Our goal is twofold. First, to predict the energy decay curve from simple room geometry and material properties, and second, to reconstruct a plausible RIR from that predicted energy decay curve. Well, energy decay curves are attractive because they are compact, smooth, and much easier for a neural network to learn than a raw RIR waveform. They also contain enough information to drive key acoustic parameters like T20, C50, and EDT. Furthermore, if we can reconstruct the magnitude of RIR and reasonably estimate its polarity, then we can obtain a perceptually plausible RIR from the EDC prediction. This significantly reduces the dimensionality of learning problem. Our main contributions are: first, we propose an LSTM-based neural network that predicts energy decay curves given only room geometry, source and receiver positions, and average absorption coefficients. Secondly, we introduce two reconstruction approaches, random sign and random sign sticky, to recover the polarity of RIR. And third, we evaluate the system both objectively and perceptually, including a full Mushra listening test. To train and evaluate our model, we simulated 6,000 shoebox-shaped rooms using PyRoom acoustic library. Room dimensions vary between 3 to 6 meters in length and between 2.5 and 4 meters in height. Source receiver distances range from 1 to 4 meter, and wall absorptions span realistic values from 0.14 up to 0.65 across all frequency bands. This variability ensures that the model encounters a wide diversity of room acoustic conditions. Here we show the distribution of T60 values across our dataset. You can see that the room range from almost anechoic to highly reverberant conditions. Such diversity is extremely important because it exposes the model to both short and long decay patterns, making it robust and generalizable. We generated RIRs at 48 kHz. For each simulated RIR, we compute the energy decay curves by integrating the squared impulse response in reverse time. The dataset is then split into 60% for training, 20% for validation, and 20% for testing. This ensures independent evaluation and avoids overfitting. The model receives 16 input features including room dimensions, source and receiver coordinates, and frequency averaged absorption coefficients. We apply min-max normalization to map each feature into the range from 0 to 1. Finally, we prepare the inputs in the shape required by LSTM model, which expects a sequence. Even in our case, the sequence length is only one-time step. Our architecture begins with an LSTM layer containing 128 hidden units. We apply dropout of 30% to reduce overfitting. The LSTM output is passed to fully connected layer of 2048 ReLU units, again with dropout of 30%. The final output layer produces the predicted energy decay curve as a regression task with linear activation. This setup strikes a balance between expressiveness and computational efficiency. We train the model using Adam optimizer with a learning rate of 0.001. The primary loss is mean squared error between predicted and ground truth energy decay curves. We also use early stopping with the patience of 10 epochs to prevent overfitting and to make training more efficient. In a second experiment, where we aim not only to predict EDC but also to reconstruct RIRs, we introduce a composite loss. The first term is the usual EDC MSC, while the second term penalizes mismatches in the reconstructed RIR magnitudes, as you can see in the formula. This encourages the network to produce energy decay curves that lead to physically plausible RIR magnitudes after reconstruction. Energy decay curves are cumulative sums of square impulse responses. So, if we differentiate the EDC and take the square root, we can retrieve the magnitude of RIR. Mathematically, we compute the negative differences between consecutive EDC samples and then take the square root of the positive part. This gives us magnitude envelope of RIR. The challenge is that EDCs contain no information about the sign of each RIR sample. To address this, we use stochastic sign methods such as random sign method, which assigns a completely random sign to each sample. The random sign sticky method, however, enforces temporally consistency by keeping the sign the same for stretches of the time with some probability. This makes the reconstructed signal smoother and perceptually more realistic. To evaluate our result, we consider several categories of metrics. For EDCs, we compute MAE, RMSE, and R-squared values. For acoustic parameters like EDT, T20, and C50, we again use MAE, RMSE, and R-squared values. For the reconstructed room impulse responses, we measure mean squared error, correlation, and spectral errors. And finally, we perform a perceptual evaluation using a Mushra listening test with 20 participants. Here you can see example plots comparing predicted and ground truth energy decay curves. As we can see in the figure, for room 93, which is randomly selected, the model captures the decay shape very closely, especially in the early and the mid decay regions. This demonstrates that the LSTM successfully learns the underlying acoustics of the room. The table on this slide summarizes our prediction error for EDT, T20, and C50. The mean absolute errors are low, typically just a few hundredths of a second for reverberation time measures. The R-squared values are very high, close to 1, indicating that the model explains almost all variance in these acoustic parameters. When reconstructing room impulse responses, we observe correlation ranging from around 0.37 to 0.52, depending on the example cases what we selected. Here we have selected 4 example cases, and the spectral mean squared error is typically between 54 and 58 decibels for our selected rooms. Although the correlation values may seem modest, the perceptual quality is surprisingly good. This slide shows the results of our Mushra listening test. The reference RIRs unsurprisingly received the highest score. The reconstructed RIRs using random sign sticky reach a mean score of about 86, which is remarkably close to the reference. Random sign performs worse because of its abrupt sign change, while the anchor behaves as expected. Overall, listeners found the RSS method highly convincing. Hence, the LSTM approach works well because input space is low dimensional and energy decay curve representation is smooth. Using EDCs significantly reduces the complexity of the learning task. The stochastic sign reconstruction might seem simple, but it turns out to be effective for generating perceptually realistic RIRs. In the future, we aim to expand the training dataset using wave-based simulations or actual measured room impulse responses. We also plan to explore transfer-based architecture or hybrid models that might capture longer range dependencies more effectively. Finally, we want to improve the room impulse response synthesis process by incorporating spectral phase models to reduce randomness. And yes, the custom loss function. Thank you for your attention.